In this video, we're going to be working some related rates practice problems. So the first one is from a recent AP Calculus exam. This was from 2025 Calculus AB, and it was part D of number 6. A particle moves along the curve h defined by the equation 2xy plus the natural log of y equaling 8. At the instant when the particle is at the point 4,1, dx dt is 3. Find the value of dy dt at that instant. Okay, so we're going to start by taking the, original relationship between x and y that they gave us and taking the derivative with respect to time. So if I've got 2xy plus the log of y equaling 8, then the derivatives of those things with respect to time would be equal. Okay. So, if I take the derivative of 2xy, that's going to be a product of 2x and 1y. And the derivative of 2x with respect to time is going to be 2 dx dt, right? Because we're taking with respect to t. And leave y the same, then add, leaving 2x the same, taking the derivative of y, because it's a product. Okay, then we're going to take the derivative of natural log of y with respect to time, and that would be 1 over y multiplied by the derivative of y with respect to time. And that's going to equal the derivative of 8, and that's going to be 0. No, that's 0. Said it right, I tried to write 8. Okay, and then we know that x is 4, y is 1, dx dt is 3. So 2 times dx dt times y, x dy dt, that's the thing we're hoping to solve for, plus 1 over y is going to be 1 dy dt. That's going to equal 0. Okay, and this is going to be a very solvable equation. So I'm going to have 6 plus 8 and 1 would be 9 total dy dt's equaling 0. And then we'll conclude that dy dt was equal to 6 divided by 9, which would be negative 2 divided by 3. All right. Number 2 is a very similar problem from 2024. I think we may have even done this one in the examples in class. Y cubed plus 2xy equals 24. Yeah, we can see the x is 4, y is 2. That y coordinate is decreasing at a rate of 2 units per second. We would need to translate that into dy dt as negative 2. All right, but first we're going to start by having y cubed plus 2xy equals 24. Notice in both 2024 and 2025 we have that 2xy in there. They really like to have you take the derivative of a product of x and y in AP Calculus for whatever reason. So we're going to take the derivative of this equation, 3y squared. We're taking it with respect to time, so y and x would both have their own derivatives with respect to t. Plus, okay, the derivative of 2x, leave y the same, leave 2x the same, take the derivative of y. And then the derivative of 24, that's going to be 0. Okay, then we've got, just write it all down off to the side, x equals 4, y equals 2, y coordinate is decreasing by 2, so dy dt is negative 2. And then we're going to say, okay, 3y squared would be 3 times 4 dy dt was negative 2. 2 times dx dt is what I hope to solve for. And y was 2. Okay, and then plus 2x would be 8. dy dt was negative 2. That's all going to add together to equal 0. All right, so I'm having negative 24 plus 4 dx dt minus another 16 equaling 0. 4 dx dt minus 40 equals 0. And okay, so dx dt has to equal 10. Right. So I've got a circle. A circular puddle of water is expanding as more rain falls. The volume of the puddle Wait a second. Yeah, that should definitely say area of the puddle. The area of the puddle is increasing at a constant rate of 0.2 square inches per minute. Wondering got that problem from, because I definitely didn't think of a circular puddle of water expands as more rain falls. That was not my idea. Okay, zero point 0.2 square inches per minute. At the moment when the radius of the puddle is 5 inches, what is the rate of increase in the puddle's circumference? That's something we can do. Okay, so we know that dA dt is 0.2. And then I've seen ones like this where it's like the puddle is like actually a small cylinder, but they're not giving us the height. And they're also not, they're saying it's expanding, so obviously, and if the area be getting bigger. Okay, anyway, the radius is 5. What is the rate of change in the circumference? All right, so I'm going to start with what we know. Area is pi r squared, and we know dA dt is 0.2. So I'm going to take the derivative. dA dt is going to be 2 pi r dr dt. Okay, then we're going to plug the stuff in and get dA dt equaling 2 pi. The radius was 5, and then dr dt was 0.2. So that's going to be 10 times 0.2 would be 2 pi. And if dA dt is 2 pi, or wait. That's not what they said. Hold up. We have dA dt equaling 0.2, so that's where the 0.2 needs to go. Okay, and dr dt, I knew that wasn't going to work quite right. Okay, so 10 pi, actually take this 2 over 10 equals 10 pi dr dt. Okay, and then I'm going to divide both sides by 10 pi, and I'm going to say that dr dt is equal to 2 over 100 pi. And I could probably make that 1 over 50 pi if I wanted, but it might be better to simplify with 2 and 100 here in a moment. We know that circumference is 2 pi times the radius. So I might take the derivative of circumference with respect to time and get 2 pi times dr dt. And then if dr dt was this 2 divided by 100 pi, yeah, then we could probably simplify like that and get 4 over 100 is 1 over 25. Okay, and if, they gave it to us as a decimal, we might be wise to give it back to them as a decimal 0.04. Okay, but that's not, mandatory at all. 1 over 25 is a perfectly fine answer. All right. The cube is growing. The volume is increasing at a constant rate of 12 cubic centimeters per minute. So derivative of volume with respect to time is 12. And we also know that for a cube, volume is equal to x cubed if x is the side length. Instant when the side lengths are 10 centimeters, what is the rate of increase in the surface area? Alright, so we'll take the derivative. Derivative of v with respect to time, well, the derivative of x cubed would be 3x squared multiplied by the derivative of x with respect to time for the chain rule. And so we're going to get 12 equals 3 times 100 dx dt. And I might divide the 12 and the 3 first. Divide by 3 on both sides. Okay, so dx dt is going to be 4 divided by 100, and that's 1 over 25. Then the area of the cube is going to be 6x squared because there are 6 sides and they're all squares. And then I'm going to have the derivative of a with respect to t is going to be 12x dx dt. And d8 dt is the thing I'm hoping to solve for. So 12x was 10, dx dt was 1 over 25. So, well, the 25's got a factor of 5, and so does the 10. So, let's say that's 10 over 25 is the same as 2 to 5. So it's going to be 24 over 5. All right. All right, now a thin sheet of metal expands and it's a rectangle. The instant when the width of the sheet, let's see, the width is 150 and the length is 200. Width is expanding, okay, so I'm going to call them x and y. Width is expanding at a rate of 5 millimeters per minute. So dx dt equals positive 5. Length is increasing at 4, so dy dt is positive 4. What's the rate of change in the area in square millimeters per minute of the rectangular sheet of metal at that instant? Okay. Area is going to equal x times y. And if we want to take the derivative of area with respect to time, we're going to need to use the product rule. So first we'll take the derivative of x, leave y the same. Then we'll leave x the same and take the derivative of y. And I think we've got all the pieces we need to plug in. We're going to say dx dt was 5 multiplied by y plus x multiplied by dy dt. Okay, so I'm going to have 1,000 plus 600 more. That would be 1,600. We've got a large spherical balloon being inflated. Its radius is increasing at a constant rate of 0.1 feet per minute. The radius of the balloon is 11 feet. How fast is the volume changing? Okay, this one will be quite a bit easier. This will only involve one formula because we can write volume in terms of radius and we can, relate those rates. So volume is equal to, for a sphere, 4/3 pi r cubed. Now that's a formula you would be given in line with a question on, say, like a quiz or a test, but on the homework, you either got your notes nearby and you got a list of formulas, or you could just look it up. It wouldn't be a big deal. So I'm not going to write all of those, and I was printing this on a single sheet, so I wasn't trying to take up any more space. Okay, and we will also need to indicate units of measure. Okay, that's good. That's been not something we've asked you to do yet. So first I'm going to take the derivative with respect to time. dv dt is going to be 4 pi radius squared dr dt. We know that 4 pi r squared is 11 squared, that'd be 121. And then dr dt was 0.1. All right, so I think that is going to be our value of dv dt, and I think I might just stop there because, 121 doesn't have a factor of 5 in it, and so I'm not going to be able to divide by 10 or anything like that. I'll just stop there. And I don't think it would be, that much better to call it 48.4 pi. Might as well just whip out a calculator and figure out what 48.4 pi actually is. So the units of measure would be, okay, we're talking about volume, so it's going to be some kind of cubic units, or feet per minute, so it would be cubic feet per minute. Right. Air is pumped into a spherical soap bubble so that the surface area increases at 10 square centimeters per second. At the instant the radius is 2 centimeters, find the radius and volume are increasing. Okay, that was unnecessary. All right, so we can do that, and so I think really what we need to do is okay, the radius and volume. Okay, so we'll probably start with the area formula. Area of a sphere is 4 pi r squared. Take the derivative of that with respect to time. And start to plug stuff in. And this will help us find the first thing, rate at which the radius was increasing. So dr dt, that would be 10 divided by 16 pi. And I might call that 5 over 8 pi. And then, interested in the rate at which the volume is increasing, we're going to start with the relationship that volume is 4/3 pi radius cubed. We'll take the derivative of that with respect to time and say, okay, that'll be 4 pi r squared dr dt, kind of like we saw in the last one. And then we have dr dt, we have r squared, so we should be able to find dv dt. So here, once I go to plug stuff in, I'm going to have 4 pi radius squared would be another 4. dr dt was 5 divided by 8 pi. So we'll have 10. All right. Now we've got a landscaping crew building a decorative sand pyramid in a park. Okay, this is going to be one where they just give you some really weird formula and you just have to go with it. So sand is being poured slowly into the pyramid in such a way that the overall shape remains constant and the volume of the pyramid is given by V equals 1/6 x cubed, where x is the side length of one side of the base of the pyramid. If the workers are pouring sand onto the pyramid at a rate of 2 cubic feet per hour, so the rate of change of volume is equal to 2. How fast is the area of the base increasing? When the area of the base is 36 square feet. Okay, so those have some layers to it. So they told us that volume was equal to 1/6 x cubed. And x is the one side length of the base of the pyramid. I'm going to try to see, can I draw a parallelogram? Yes, I can. No, I think that actually needed to be a lot more stretched out in order for this to look right. To try to stretch it a little more. Okay, yeah. And then, I don't know, I've never tried to draw a pyramid before, but I'm just going to go with it. Okay, that looks pretty decent to me. So what we're saying is that those are the side lengths of the base, and somehow the height works in such a way that the volume is just perfect. So the area of that base and the side will need to be coming in front for sure. The area of that base is what we're interested in, its rate of increase. So if the area is 36, that does mean that x is going to equal 6. Okay, I can see that. That'll be the first thing. And so I think I'm going to take the derivative of volume with respect to time and get 3 over 6 x squared dx dt. And we have dv dt. Okay, yeah, we have what we need. At least to get to the next step. So dv dt was 2 1/2 of x squared is 36, so 18 dx dt, meaning dx dt is 2 over 18, 1 over 9. And then we're going to say, okay, well, the area of the base of the is x squared. And then if we took the derivative of that, have 2x multiplied by dx dt. And we know that 2x is going to be 12. dx dt was 1 over 9. So 3, 6, 9, 12. This is 4/3. An isosceles right triangle. So that's some terminology we're going to need to know in this class for a thing we're going to do later on, probably in a couple months from now. So an isosceles right triangle is kind of a not successful. Okay, that's probably something I can work with. It's what, in pre-calculus you might have called a 45, 45, 90 triangle. It's half a square. And that's what we're mainly interested in this class, is just the fact that its area is 1/2 x squared. So the legs of the triangle, we do have x and x. We do also know from pre-calculus that the hypotenuse is root 2x. I'm just going to put that there. And then maybe also we know that the area of this triangle is x squared divided by 2. I might just write that 1/2 x squared because we're going to want to take the derivative of it, and 1/2 will go away. Okay, so they say the legs of the triangle are 10 meters. Area is decreasing 10 meters per minute. So dA dt equals -10. What's the rate of change of the length of the legs, and what's the rate of change in the length of the hypotenuse? All right. So let's say if we take the derivative of a with respect to time, we'd get 2/2 x to the first dx dt. Okay, and they told us the dA dt was -10 equals 10 dx dt. dx dt must be -1. Okay, so that's the rate of change in the length of the legs. And then as far as the rate of change in the length of the hypotenuse, we could call that h. H equals root 2x. Well, if we took the derivative of that relationship with respect to time, we just get, okay, root 2, the derivative of x is 1, dx dt. And I just determined that dx dt was -1, so dH dt is going to be negative square root 2. Okay, next we're going to move on to a semicircle. It's another shape that we work with once we start to do areas and volumes later on with the integrals. So okay, that's my best rendition of a semicircle. The radius of the semicircle is going to be 6 feet. Actually, that's subject to change. We're interested in the moment when r is 6. The radius is decreasing 0.5 feet per second. What is the rate of change in the area of the semicircle? Okay, so say the area of this thing is half of pi r squared, because it's a semicircle. Okay. And then, okay, take the derivative of this with respect to time. Get 2/2 pi r to the first dr dt. And then I'm going to plug in the pieces. Okay, we're solving for dA dt. So dA dt at the time we're interested in is going to be pi times radius times dr dt. So that would be -3 pi. Right? The area of a quarter circle is decreasing at a rate of 1 square unit per hour. What is the rate of change in its radius when the area is pi? Okay, so I've got a... I need to take a second. I knew a quarter circle is beyond my usual drawing skills. So the area is decreasing 1 square unit per hour. Okay, so dA dt is -1. The area of this thing is going to be a quarter of pi r squared. Let's say quarter of a circle. And then they told me dA dt was -1, and that the area was pi. Okay, so if the area is pi, that means that r squared had to be 4, so that would be radius equaling 2. And then, what is the rate of change in its radius? Okay, well, we're going to take the derivative of this relationship right here. Derivative of area with respect to time is going to be 2/4 pi radius to the first dr dt. And then I know dA dt was -1 equals 1/2 pi. I'm just going to write that as pi over 2. R was 2 dr dt. Okay, that's going to leave dr dt being -1 divided by pi. Right? These are a couple of nice right triangle problems. The triangle shown at right, theta is increasing at a constant rate of 2 radians per minute. Okay, so I'm working number 12 right now. Okay, so d theta dt equals 2. When y equals 5 miles, so y equals 5, that will mean x equals 12. Rate of change in y. So dy dt is equal to what? Okay, so what we should probably do is get, since I have d theta dt and I want dy dt, I need to start with a relationship that connects theta and y. And I also, we're saying 13 is fixed, even as theta increases at a constant rate of 2 radians per minute. So basically the triangle is going to get taller and taller, and then I don't know what's going to happen. I guess x is going to go negative for a while. So maybe x is just going to be, y is 5 miles. This is a huge triangle. Maybe we're just thinking about it as going west of the original point or something. So, okay, what we need is a relationship between theta and y that could also use that 13. And so I'm going to use sine. So I'm going to say sine theta. And it's not that you couldn't do it with y and x, but you might actually need... Oh, wait. I misread the problem. We want dx dt. So I should not be using sine. That would give me dy dt, and that wouldn't be all that helpful. Okay, so if I made an error, and I'm kind of restarting on this problem. So y equals 5, that does mean x equals 12, because it's 5, 12, 13 triangle. D theta dt is 2. We want to know what dy dt is. So I need to use sine because that's a relationship that connects y and theta, and would also use the 13, really taking advantage of the fact that 13 is fixed. So sine theta is going to equal y over 13. And I would recommend you rewrite that relationship as sine theta equals 1/13 of y, because it's a little easier to take the derivative of, I think, especially for a first-time calculus student. And so if we take the derivative of this expression with respect to time, we take the derivative of sine theta, which would be cosine theta, times the derivative of theta with respect to time. That's going to equal 1/13 of the derivative of y with respect to time. That's dy dt. And I've got all the pieces I need to figure out cosine theta. Okay, I know that x equals 12 at this moment, and so cosine is going to be 12 over 13. So 12 over 13 d theta dt was 2. That's going to equal 1/13 of dy dt. And dy dt is what I'm hoping to solve for, but I'm just looking at this equation and I'm saying, oh, okay, dy dt is going to have to equal 24. And because of the 13s being the same on the denominator, I need the numerators to be the same because it's going to be 24 there. So dy dt equals 24 miles per hour. And then for number 13, I'm going to Say, all right, the thing we changed is, okay, y is equal to 12, and then that means that x is equal to 5. What's the rate of change of x? But d theta dt is still 2. So we said number 12, theta is just increasing a constant rate of 2 radians per minute at all minutes. Okay, so d theta dt equal positive 2, and okay, at this point, if we want dx dt, then I'm going to want to use cosine. So cosine theta would equal x over 13. I'm going to call that 1/13 of x. Then we're going to take the derivative of this with respect to time. Plug in what we know. Sine theta would be y over 13, so negative sine theta is going to be negative 12/13. D theta dt is still 2. And then this is going to be 1/13 of dx dt, and it's like, oh, it's working out the exact same way as the other one. And at this moment, dx dt is going to be negative 24 miles an hour. Just got a couple of scenarios left. This one is one where we've got two objects moving along the x and y axes. Okay, and we can definitely ask some related rate questions about these objects, like particle motion questions. So object A moves along the x-axis and B is along the y-axis. So I'm going to just draw a little diagram. It's going to be my y-axis, my x-axis. So, all right, x is at 40, so object A is over here at x equals 40. And object B is at y equals 9. And we could ask about, the distance between the two objects. Are they moving toward or away from each other? That's not really a question I'm asking anymore. There was some discussion on that last year in my class, and we decided that it would be much clearer to ask, is the distance between points A and B increasing or decreasing at this time? Okay, so I'm going to go back in and edit that. There have been a few things on this homework. It's new homework, though, and I just kind of published it, made the copies, and thought I'd catch the errors when I worked it. So we're going to figure out if the distance is increasing or decreasing, and then we'll also think about the area of the triangle formed by the origin A and B. So we're really going to be thinking a lot about this triangle right there. Put the third vertex right there, but I think you see what triangle I'm talking about. So the for number 14, I think I'm going to say, all right, the distance, what I know about that is, like, we're thinking about the sides of the triangle, and so that's x squared plus y squared equals r squared. That's the relationship I'm going to want to take the derivative of. Okay, because I know the velocity of object A, that's going to be dx dt. The velocity of object B would be dy dt. Dr dt is going to be telling me if the distance AB is increasing or decreasing, because r is that distance. Okay, so if I take the derivative of this, I would get 2x dx dt plus 2y dy dt, and that would equal 2r dr dt. Okay, and then I'm going to just kind of plug in all the pieces. 2x would be 80, dx dt is 2, 2y is 18, dy dt negative 12. That's going to equal 2r. Now, I know that r is going to be 41 because I know that 9, 40, 41 is a Pythagorean triple. You could go and figure it out yourself, or you could say, okay, well, this distance, we're going to say this distance is positive, so 2r is going to be a positive number. I happen to know that 9, 40, 41 is a triple, so I'm going to put that in there. And dr dt, but somehow that's not going to impact the sign of our result for dr dt. Really, what's going to happen is right there. So that's what's going to determine whether r is increasing or decreasing. So I'm going to have 160 minus 12 times 18, which I know is a negative number, so I'm not even going to worry about it too much. I'm going to solve for drdt, and zoom out a little bit so I can write underneath it and say decreasing because drdt is negative. For number 15, talking about the area of the triangle. Okay, so we would know that the area of this is going to be 1/2 base times height. So that would be 1/2 x times y. We can take the derivative of this with respect to time. That would be the derivative of 1/2 x. Leave y the same. Then leave 1/2 x the same and take the derivative of y. So we will plug in the pieces and say, all right, 1/2 dx dt was 2 and y was 9, plus 1/2 x was 40 and dy dt was negative 12. And I make an error here. No, just must have changed up some numbers. Usually I've made a bunch of versions of this problem where, but usually one is increasing, the other one's decreasing. But this one, it's the numbers are in such a way that they're both going to be decreasing. All right, so the difference in velocities is kind of, I think, telling. Okay, anyway, so I would say that that's a suitable expression if it's a quiz, and in fact I can see that this is clearly a negative number. Negative 40 times 12 is really big, and 9 times 2 is 18. So I'm going to say decreasing because dAdt is negative. All right, and the last problem we've got is the sliding ladder scenario, which that's always going to come up in Cal 1 class. So a 5-meter ladder is sliding down a wall. And so the hypotenuse of the triangle is going to be 5. At a certain instant, the top of the ladder is 4 meters above the ground. Okay, this is 2 different problems, so I should probably make 2 separate diagrams. Top is 4 above the ground, so it's a little taller. All right, so that's going to be a y equaling 4, but only temporarily. Okay, and it's a 5-meter ladder, so x is going to be equal to 3. Okay. The top is moving down the wall at a rate of 0.4 meters per second, so that would be negative 0.4. At what rate in radians per second? Okay, so I'm looking for d theta dt is the acute angle between the bottom of the ladder and the wall. That's right there. Changing at that instant. Okay, so if I've got dy dt and I want d theta dt, again, kind of like this other one with the triangle, I need to use sine. So I'm going to say sine theta is equal to y over 5. I can't say sine theta is 4/5 and take the derivative of that, because that's subject to change, right? Sine theta is not always 4/5. Sine theta is just temporarily 4/5. So I'm going to say sine theta is y over 5, which is 1/5 of y. And then at any time t, cosine theta d theta dt is y dt. Okay, and that's where we'll be using the fact that dy dt is negative 0.4. So cosine theta d theta dt, so cosine theta would be 3/5. That's going to equal 1/5 of dy dt, and dy dt is negative 0.4, but that's negative 2/5, and that might be helpful, or maybe not. I don't even know. Man, this is the type of place where you could be making errors. I'm gonna just take this one slowly and multiply both sides by 5. So negative 10, I had 25 in the denominator, but I'm going to be dividing by 3, and so that would be 75. Okay, obviously there's common factors of 5 in there, so that would be negative 2 over 25. Which, no. Negative 2 over 15. Yeah, I don't know, that's a little more like it. Okay, so that's d theta dt at that instant. And then number 17, let's say, at a later instant, the top of the ladder is 3 meters above the ground, so it's more like this. Oh, whoops. Yeah, I would like to write y equals 3, x equals 4, because those are both subject to change, and the length of the ladder is still 5. And, okay. The bottom of the ladder is moving away from the wall along the ground at a rate of 2 meters per second. So dx dt is 0.2. At that instant, what is the rate at which the top of the ladder is sliding down the wall? Okay, so dy dt is equal to what? Okay. Now, I think if I want a relationship between x and y, and I don't really have any information about theta in that moment, which it seems like they're saying a later instant, and the rates are kind of different. So I don't. Yeah, the rate that the ladder was moving down the wall in number 16 is not going to be the same as number 17. Obviously, that's the reason it's a different question. So I think what I need to actually use is the Pythagorean theorem. I think because that would make use of the fact that the 5 is fixed and also incorporate both x and y. So I'm going to say x squared plus y squared equals 5 squared. Take the derivative of this with respect to time. Say, all right, now I can just kind of put in the pieces. 2x dx dt would be 8 times 0.2 plus 2y would be 6 dy dt. That's going to equal 0. All right. Okay, so 8/5 is going to subtract. Okay, and then that's going to... So, 8 over 6 times 5, so 4/3, so 4 over 15. All right, and that's it, right? Yes, all right. So that's all the problems on this homework, so that's all for this video. Thanks for watching.